Welcome to HotChips 18. Session 6, Embedded Processors.
Okay, so as I said, my name is Chuck Moore. Right now I'm not involved with embedded processors, but I have been involved with embedded processors in the past, and it is an area that I continue following. We have 4 talks today. The first talk will be given by Arjan Bink, who is from Handshake Solutions. The title of the talk is the ARM996HS, the first licensable clockless 32-bit processor core. Let's see, Arjan graduated from Eindhoven University in 1995, joined Philips Research at that point, migrated eventually to Philips Semiconductor, and then in 2003 became Chief Design Engineer at Handshake Solutions. Handshake is part of the Philips Technology Incubator Program. So please welcome Arjan Bink.
Good morning, everybody. So my name is Arjan Bink, and I will present the ARM996HS, the first licensable clockless 32-bit processor. First, a little bit of background. This ARM996HS is a joint development between ARM Limited and Handshake Solutions. So we are jointly developing clockless processors aiming at very low power, low electromagnetic emission, and high robustness. The potential application domains are those where the needs for this low power, this low peak currents, and the low emission converge. For example, automotive, low-cost battery-operated devices, and wireless. Handshake Solutions and ARM jointly market and promote the ARM996HS, and the licensing is done by ARM Limited themselves. This slide gives a brief summary of the entire presentation, I would say. So one of the key features of this clockless or asynchronous ARM core is its power efficiency. So this slide gives you the drystone MIPS per watt, so the power efficiency of the processors. All the processors shown in blue are ARM9 cores executing the same instruction set. So they all execute the ARM v5-TE instruction set, and they all contain a similar 5-stage integer pipeline. You can see that the clockless ARM996HS is almost a factor 3 more power efficient than the best clock-gated synchronous ARM core, the ARM968. The remainder of this presentation will consist of 3 parts. In the first part, I will explain a little bit about the underlying technology that we use to implement this processor, so-called handshake technology. In the second part, I will briefly introduce the functional features of this ARM core, and in the third and last part, I will give some benchmarking results. So first, something about the underlying technology. This ARM996HS core is based on handshake technology. Handshake technology is a design flow for clockless digital ICs. The design flow starts with the so-called HASTE program. The HASTE program is a C or behavioral Verilog-like program which is compiled down to a so-called handshake circuit. Handshake circuit is a circuit consisting of based on a library of about 50 handshake components. This circuit is then mapped onto a regular Verilog netlist containing for 100% out of standard cells. This handshake circuit, this Verilog netlist is then made scan testable, and from there on we use standard EDA tools for the whole backend process. So our tool flow will output a Verilog netlist mapped to your standard cell library, and we will provide scripts for standard EDA tools like the ones from Synopsys, Cadence, or Magma for place and route, test pattern generation, static timing analysis, simulation. The design flow is an industry-proven design flow. We have dozens of chips in the market, for example, in the automotive domain and also in the identification domain. More than 100 million ICs have been sold. Although we do license this design flow to the industry, in case of an ARM delivery, the licensee will only receive the netlist together with all the backend scripts for the standard EDA tools. So in case of an ARM delivery, this design flow is completely hidden for the licensee. Something more about the technology. So instead of using a global clock, all modules communicate by means of handshakes. And a handshake is a combination of alternating request and acknowledge signals. We use a so-called four-phase handshake signaling, and the request and acknowledge signals can encode data. The data path consists of a single rail circuit, which is the same as in regular synchronous circuits. So this already implies that if your circuit is dominated by the data path, you can expect our clockless circuits to be roughly the same size as a comparable synchronous circuit. In general, a handshake technology netlist, so also the ARM996HS, looks like the following. It always consists of two parts, control part and a data path part. In the control part, we have the asynchronous handshaking going on. It typically consists of Muller-C elements, and the data path is very similar to a synchronous data path, with the exception that we have an easy way to use latches in this data path. The logic in the data path is being matched by so-called delay chains. So for example, if this circuit is the ARM processor, the logic block number 2 can be the ALU of the processor, and it's being delay matched by, conservatively being delay matched by delay chain number 2. Our tool flow, the split in control and data path is fully automated, so our tool flow takes care of the split, and it takes care of generating scripts for tuning those delay chains, even all the way down to place and route and timing sign-off. So now I come to the second part of the presentation, the functional overview of the ARM996HS. Well, basically, it's a regular ARM v5-TE architecture, just like all the other ARM9 cores. There's a 5-stage pipeline, and it fully supports the thumb instruction set and the DSP extensions. It's a Harvard architecture. It has dual tightly coupled memory interfaces and dual synchronous AHB interfaces. There are some extra features not found in other ARM9 cores, which are indicated in blue here, so the dual AHB interfaces, the non-maskable interrupts, an enhanced memory protection unit, and a hardware divide unit. I'll come back to those features in later slides. So if we zoom into this picture, we get something like the following. This slide will show the major internal and external interfaces of the ARM996HS. First, I will briefly explain the blocks. First of all, there's a regular 5-stage pipeline being controlled by a pipeline controller. There's a system controller for loading and storing data and for fetching instructions. There are internal coprocessors, a debug unit for setting breakpoints, watch points, all that kind of stuff, and a sample unit for handling interrupts and debug requests. The lines in blue are so-called handshake interfaces. So each blue line represents two signals, a request and an acknowledge. The pipeline is controlled by the pipeline controller. The pipeline fetches its instructions and data via handshakes to the system controller. And because this communication is based on handshakes, for example, if an instruction is not ready or data is not ready from the system controller, the pipeline will automatically stall, so there's no need for explicit wait states. JTAG is also based on handshakes, and there are two more interfaces that I will come back to in a later slide. The tightly coupled memory interfaces here on the left. We handshake to those scratch pad or tightly coupled memory ramps, and a so-called tempo interface for throttling the performance of this ARM processor. The second type of interfaces are the so-called asynchronous data interfaces. We use them for interrupts and debug requests. Handshake technology has a so-called wait construct, where you can wait for a certain event to happen, or you can wait for a certain level on a signal without actually having to pull for that data, like you would do in a synchronous system. We use this to implement a truly zero active power wait for interrupt mode. So the processor can be in a sleep mode without the need for any clock running to pull for an interrupt. The third type of interface are the so-called clocked interfaces. In this case, there is a clock signal, but it only goes to the bus interface of the ARM processor. So basically, we provide a synchronous bus interface to allow for easy integration into a synchronous system on chip. If we zoom in even further to the pipeline, you see that we have a regular 5-stage pipeline, very similar to the one found in synchronous ARM9 cores. So it has a fetch, decode, execute, memory, and write back stage. The pipeline is controlled by a controller by means of five handshake pairs. So again, these are 4-phase handshakes controlling the operation of the pipeline. The pipeline control has been implemented in such a way that the pipeline stages are always activated in a distributed way. So no pipeline stages are ever clocked at the same time, and we did this to reduce the peak currents, as you will see in the benchmarking section. So this entire pipeline then again handshakes to the system controller for fetching instructions and data. The next 4 slides are about the features which are special compared to other ARM9 cores. So first of all, the dual HB light interface. There's one interface for instructions, one for data. We made the decision to implement the boundary of this interface in a synchronous way. So you can easily put this ARM into a regular synchronous multi-layer HB system. The second special feature is the enhanced memory protection unit. Compared to other ARM9 cores that have an MPU, this MPU has a much finer granularity. The granularity is only 32 bytes instead of 4 kilobyte, instead of a 4 kilobyte granularity as found in the ARM946. It's a unified 12-region MPU. The third special feature is a so-called hardware-defined coprocessor. We implemented signed and unsigned 32-bit division by means of an internal coprocessor. The coprocessor runs in parallel to the pipeline, so you can schedule instructions while awaiting the result of this division. It takes about 13 equivalent cycles to execute, compared to 36 cycles for a synchronous ARM core implementing this divide in software. And last feature that is not found in other ARM9 cores is nonmaskable interrupts. So a nonmaskable interrupt is an interrupt, in this case the NFIC interrupt, which cannot be masked by software. It is handy for applications, for control applications, where you need very high reliability or high availability. You can, for example, use it to map your, let's say, a signal indicating a low battery life, something like that. Now I come back to 2 of the interfaces that I skipped on an earlier slide. First of all, the tightly coupled memory interface. The tightly coupled memory interface, or the scratchpad memory interface, has been implemented by means of a handshake channel. So this means we handshake with the memories. The ARM996 issues a request or clock to the memory, as seen here on this red waveform, and then it waits for the memory to respond with the corresponding acknowledge or ready signal. The timing works like this. The rising edge of the request or clock line indicates that the address, control, and write data information is valid. And then as soon as the memory corresponds with the rising edge on the acknowledge or ready signal, the processor knows that the read data and or error response is valid. So in this way, we can interface to synchronous RAMs in a glueless way. Furthermore, the ARM automatically adapts to the native speed of the memory, and there's no need for explicit wait states. Also, the memory is only being clocked when needed, so only when the ARM actually wants to do a tightly coupled memory fetch, the memory is being clocked, and this clocking of the memory is not aligned to any global system clock, so again the peak currents are being reduced. The second interface that I skipped, the so-called tempo interface, requires a little bit introduction. Asynchronous or handshake circuits in general automatically adapt to changes in environmental conditions like temperature, supply voltage, or supply current. We think this is a very good idea, so this makes your circuit very robust, and the circuit will continue to operate over ranges in which a synchronous core could break down. So for example, if you have a voltage drop out of spec, in our case, the ARM996HS's logic, including its delay chain, would just slow down, but the processor would still operate correctly. Whereas in a synchronous design, as soon as your voltage is out of spec and your circuit no longer fits in the clock period, you can have a malfunction. The downside of this is that it is hard to mimic worst case conditions. And you can, for example, want to do that when you're developing software in a lab. You want to push the processor in a worst case condition so that you're sure that your software always fits. We countered this problem by the introduction of a so-called HD matrix peripheral. Basically what we did is we have this so-called tempo interface, which is a handshake, and every time the ARM processor executes or activates its execute stage, it performs one handshake over this channel. Then this external matrix peripheral can use this handshake in basically two different ways. First of all, it can use this handshake and synchronize it to an external event, for example, a clock. So in that way, you can synchronize any number of handshakes, and basically you can synchronize the pipeline to an external event. So you can synchronize n instructions to n clock events. In the second way, you can non-intrusively monitor the performance of the ARM processor by just counting the number of handshakes. In this way, the matrix unit can be used for advanced power management or for pushing the ARM processor into its worst case corner for software development. Now I come to the third and last part of this presentation, the benchmarking section. First of all, there's one slide about functional benchmarking. Compared to other, so this slide compares the ARM996HS to some of the other synchronous ARM9 cores and to the ARM7. All of the synchronous ARM9 cores are based on the same V5TE instruction set, so they all support the thumb instruction set and the DSP extensions. They all have a very similar pipeline, 5-stage pipeline. The ARM996HS is most comparable to the synchronous 968, which is the, let's say, the most low-end ARM9 processor out there. Compared to that processor, we have a couple of things extra. There is a hardware divide unit, nonmaskable interrupts, the memory protection unit, and the dual AHB interface. But other than that, it's pretty similar. This slide gives you the power performance and area numbers of the ARM996 compared to the synchronous ARM968. Although the ARM968 can run at about 200 megahertz, in order to enable a more fair comparison, we use the layout based on a synthesis run for only 100 megahertz. So the power and area numbers are a bit more realistic for comparison. So we synthesized 968 for 100 megahertz. The ARM996HS has a relatively low performance, so it's 50 equivalent megahertz worst case, 77 megahertz in the nominal case. When we talk about megahertz, because the ARM doesn't really have a clock, what we mean is one equivalent, or the equivalent megahertz, is the rate a synchronous ARM processor would have to run to finish a certain application in the same amount of time. The area is roughly the same. So although we have an additional memory protection unit and hardware divide units, together about 15 kilogates. The area is only a little bit larger, so that's very competitive. The power is really a lot better, so it only uses 0.045 milliwatt per megahertz, which is almost a factor 3 less than the best clock-gated synchronous ARM9 core. All the numbers are based on post-layout simulations in the Artisan SageX.13 TSMC library. Basically, the power, performance, and area were not the main design criteria for the development of this processor. The main criteria were very low peak currents and low electromagnetic emission. So the next slides are about that. In general, digital circuits generate voltage noise on power supply lines and induce currents in the silicon substrate, both of which can interfere with analog circuits. Furthermore, digital circuits emit electromagnetic emission that can interfere with nearby radio signals. If we look at this, if we look at supply current in the time domain, you get something like this. Basically, in a synchronous circuit, your activity will be maximal shortly after the active clock edge, and then it will fade down in time, awaiting the next arrival of a clock edge. This can cause local drops in supply voltage, which can have an impact on performance and circuit reliability. If you look at this picture, but then based on actual simulations, you get something like this. Both pictures show the peak currents and cumulative energy for the execution of 5 dry zone loops. And you can see that both processors, the synchronous ARM996 on the left and the Handshake 996 on the right, they both execute the 5 dry zone loops in 34 microseconds, so they both run at the same performance. The figure on the left is the clock-gated synchronous core. You see that the peak currents are about 35 milliamps, and that this is about a factor 2.4 higher than the peak currents in the clockless or asynchronous core. Of course, these lower peak currents make it easier to integrate such an asynchronous core together with analog circuits. The blue diagonal line is the cumulative energy for the execution of the 5 dry zone loops. You can see that the energy for this application is a factor 2.8 lower. If you look at this picture, you might say, well, the peak currents for the synchronous core aren't that bad. I mean, they're always between 27 and 35 milliamps. But if we actually zoom into this picture, you will see that it is a bit worse than that. Actually, the peak currents always go all the way down to 0. So basically, for this graph shows the execution of 5 instructions, both again on the synchronous ARM processor and on the asynchronous one. Basically, before every rising clock edge, you see that the current is at 0, and then the clock tree kicks in and you get a high peak current. So the current always swings between 0 and, let's say, 25, 35 milliamps. In the clockless case, the current is much more constant, and typically it's around 2 milliamps. And this is really the worst case found in this simulation. Another way of looking at this is showing a histogram, what we do here. So this is just another way of showing that in the clockless case, the current is typically between 1 and 5 milliamps. So 90% of the time, the current is below 5 milliamps, whereas for the synchronous case, 90% of the time, you're in this region, from 0 to 20 milliamps. Instead of looking at the peak currents in the time domain, you can also look at the current in the frequency domain, and you get a picture like this. Again, the synchronous ARM996 on the left and the clockless ARM core on the right. In the synchronous core, you always see the clock frequency and all its harmonics. In the clockless case, you see that there is a lot less emission, so this obviously can help if you want to integrate, if you have a nearby RF circuit. Then I come to the conclusions. The ARM996HS is fully ARMv5 TE compatible There's some advanced features compared to other ARM9 cores, the dual HB light interfaces, the enhanced MPU, hardware divide, and non-maskable interrupts. There's very low gate count, very low power, almost a factor 3 lower than the best clock-gated synchronous ARM9 core. Low peak currents, low emission, zero active standby power with an immediate wake-up from interrupt. And it's very robust against changes in voltage, temperature, and supply currents. And finally, the processor is being delivered as a firm core. What we mean is we deliver it as a netlist mapped to the customer's standard cell library. We deliver the scripts for standard synchronous EDA tools to do your own layout. It's fully scan testable. It reaches about over 99% coverage there. You do not need any special cells, no special memories, no custom circuit design. It's available now from ARM Limited, and it's fully supported by both the compiler tools, compiler, linker, assembler, stuff like that, and also it's fully compatible from the debug point of view. So you can use the existing ARM tools to set breakpoints, watch points, single step, all that kind of stuff. Thank you very much.
We do have some time for questions.
Yes. I know you didn't design it particularly for the low power features, but what, in your opinion, makes it lower power? What features and how does that manifest itself?
Okay. I hope I fully understood the question. What makes it more low power?
Yes.
Well, basically, the way I always look at it is that we do really extreme clock gating. So instead of having a synchronous design where you start out with a fully clocked design and then you try to be clever and shut down parts of the design that you do not need, we start exactly from the opposite way. Nothing is active, and the handshake circuit automatically only enables the parts that should be active. So you can think of it as really extreme clock gating. Of course, the power savings, because we save almost a factor 3, that cannot entirely be in the clock tree, because there's not that much power in the clock tree. So we also took care of stuff like operand isolation and minimizing glitching, stuff like that. But we all did that at the haze level, at our design entry language.
And now, what about leakage?
Leakage will be the same, because that's really process dependent, and we do not do anything special there. Of course, you can use your high VT cells or mixed VT, just like you would do for a synchronous design.
Everything in your design is static. You can run it down to 0 frequency.
Yeah, so it's just based on regular CMOS standard cell libraries. Yeah.
On the tell me a little bit about the design process. In standard synchronous design, you have to go through this timing closure process. What is the equivalent design process for you?
Okay. Well, the good thing is basically we have immediate time and closure. The thing we have to do is make sure that that those delay chains match the actual circuit. So we provide scripts for the backend tools to automatically increase or decrease the length of the delay chains to the actual circuit. So you can put constraints on your logic blocks, and then our scripts automatically take care to instruct, let's say, Encounter or Astro or Blast Fusion to scale the delay chains to, let's say, 20% overhead. So, and then that means you have time closure, and it means that if you, for example, have a long path in a part of the design which is not really critical, let's say in in the coprocessor 14 or 15, you don't spend any time on that because it's really not relevant for the actual performance of the processor. So you only concentrate on those blocks that you know are typically being used in your design.
Thank you.
Over here.
Okay, Core Chips Nakamura. My question would be related to the previous one, but you compare the handshake with Clockless ARM, okay? But at that time, maybe low current peaks, that could be probably the dominant power consumption could be active power. Is that right?
Sorry, can you repeat the last part?
Yes, you don't mention the page number, but you compare the low power peak, low current peaks of handshake ARM996HS with clock gated.
Right.
Is okay? And in here, that probably this could be a dynamic power.
Right, true, yeah, it's active.
Yes, as a
dynamic
dominant power consumption.
Yeah.
Yes.
Yeah, so we did not look at leakage in these graphs.
Okay.
It's just active power.
But these days, probably these days, static power, power leakage, very important.
True, I fully agree. So the numbers I showed were for a 0.30 micron process where it's less relevant, but of course, going down to newer technologies, leakage becomes more important.
Right.
And you can just do a mixed VT design. You can power down this entire processor just like you would do in a synchronous design. So you can have just do power gating if you want to reduce leakage.
Okay, thank you very much.
Okay, thank you very much, Arjan.
You're welcome.
So the second talk this morning is entitled the MIPS 34K Processor, Ultimate Design Flexibility for Embedded Applications. And the speaker is Ryan Kinter. He was a lead microarchitect on the 34K. He's been with MIPS for about 10 years, going way back to the SGI timeframe. He's got a BSEE from Southern Cal, and it's his first time presenting here, so please give a warm welcome for Ryan.
Thanks, Chuck. As you mentioned, I'm Ryan Kinter from MIPS Technologies. I was the lead microarchitect for the MIPS 34K processor core family. Today we're going to be unveiling support for simultaneously executing 9 threads on this core. I'll explain how this hardware can be put to use and show why this helps the core provide ultimate design flexibility for embedded applications. I'll begin by going over the core's multi-threaded architecture. I'll then describe a few system applications that can take advantage of the core's capabilities. I'll then discuss some of the microarchitectural features that enable this usage, and I'll wrap up with some statistics on the 34K. 34K is based on the 24K/24KE core pipeline. This underlying design has been licensed by more than 20 customers and has a proven silicon track record. The primary change from the 24K is the implementation of the MIPS-MT application-specific extension. This architectural extension defines the new state and instructions to provide support for multi-threading on the core. The 34K also features the DSP extensions that were introduced on the 24KE core. These extensions allow the ALU and multiplier to efficiently process SIMD and fractional data types. The core was first released to customers in October of last year, and by May of this year, our lead customer had working silicon running 5 threads. 34K core supports configuration options of the 24K, such as cache and TLB size, plus additional options specific to multi-threading. The general purpose policy manager and gating storage modules can be replaced with custom modules that are tuned for particular target applications. Additionally, the core can be configured with 1 or 2 virtual processing elements and from 1 to 9 thread contexts, and I'll explain what these are in the next couple slides. A thread context, or TC, is the hardware associated with a software thread and can be thought of as executing the instruction stream. A thread context contains user program state, such as the general purpose register file, the MDU accumulators, and the program counter. The inclusion of an address space identifier enables each TC to be working in a different address space and therefore on a different process. 34K core can include 1 to 9 TCs, and each incremental TC adds about 10% to the base core area. The low cost and large number of available TCs makes it feasible to dedicate them to specific critical tasks. This can be particularly powerful in embedded applications that spend their lives running fixed tasks. A virtual processing element, or VPE, contains the system coprocessor state. This is the state required for processing exceptions and managing the cache, as well as the TLB array and control logic. When taken with the TC, a VPE looks like a complete MIPS 32 processor. 34K core can be configured with 1 or 2 VPEs, and depending on the TLB size, the second VPE adds 15 to 20% to the base core area. Because a VPE contains the complete privileged state, each one is capable of running an independent operating system. This makes it possible to run 2 OSs without any of the overhead associated with virtualization. Many multi-threaded architectures replicate all of the processor state per thread. For MIPS, this would be both a thread context and a virtual processing element. In this model, each thread appears to all software like an independent processor. The MIPS MT architecture, however, defines TCs and VPEs independently to allow a lighter weight multi-threading model. Multiple TCs can be bound to a VPE and run multiple programs under a thread-aware operating system. Sharing the VPE state across multiple TCs greatly reduces the per-thread hardware costs. An example of this is that a thread context alone takes roughly 1/3 the area that a thread context plus a virtual processing element will take. We have previously presented on some of the benefits of multi-threading. This is focused on its abilities to improve the pipeline efficiency. Interleaving instructions for multiple threads allows short-term pipeline bubbles, such as load to use delay and branch mispredicts, to be filled with instructions from other threads. Additionally, during long-term stalls, as might be caused by a cache miss on a load, the other threads can continue running and keep the pipeline full. These traits work to increase the pipeline efficiency by keeping the pipeline busy and improving the average number of instructions per cycle that the core executes. Today, I'm going to focus on a different aspect of multi-threading. This is the idea that by dedicating hardware resources to particular threads, it is possible to reduce or even eliminate the need to switch tasks in software. This improves the performance by reducing the total number of instructions that need to be executed. Additionally, the instructions that are eliminated are the ones that would execute between a system event and reacting to it, so this can also improve response time. Now to see this in action. One usage model is to have a one-to-one mapping of processes to thread context. In many embedded systems, there are only a small number of tasks, and it's possible to have a thread context for each one. This means that you would never need to do a context switch. The elimination of the instructions associated with the context switch increases performance and reduces power consumption. An example application where this is possible is one processing parallel data streams. There can be one control TC and up to 8 slave TCs dedicated to processing the data. It is not uncommon for the data channel to require data from an external source and spend large amounts of time waiting for it. With multi-threading, other TCs can continue executing and keep the pipeline busy. In many systems, however, you may not know how many processes there are, or there may be more than the number of TCs. In this case, a hybrid scheme can be used. Critical tasks are given dedicated TCs, and the remaining tasks are switched in and out on the remaining TCs. An example of this type of system is shown in the following figure. This shows a system targeted at a residential gateway. On the left-hand side, we have a multitasking operating system, such as Linux, running programs on multiple TCs within one VPE. This can be running the various residential gateway tasks, for example, the IP stack, firewall, and VPN software. On the right-hand side, we have a thread-aware real-time operating system, such as ThreadX, that is running the voice-over IP software. Here, there are a limited number of functions, encoding, decoding, and echo cancellation, and each one is given a dedicated TC, which means that on this side, there's no context switching going on. One additional thing to note here is the quality of service block. This represents the customizable policy manager. This block can control the relative priority of the different threads and ensure that critical threads are given sufficient execution bandwidth. The interface to this block includes information on the current state of each of the TCs and indications of instructions issuing and completing. This provides a feedback path that allows the policy manager to dynamically adapt its policies based on the real-time conditions within the core. Moving into another example, an additional use for more hardware threads is having threads that are dedicated to servicing interrupts. In this simple example, there are two threads. Thread A is your normal application code, and thread B is the interrupt service thread. This thread goes through some startup code and then goes into a waiting state, watching for an external event. While waiting for this event, thread A is able to run. When the external event occurs, thread B springs back to life and quickly services the interrupt. Upon completing the servicing, it goes back into a waiting state and thread A resumes execution. Alternatively, you could choose to continue running your application code in parallel with the interrupt service thread, allowing you to take advantage of the pipeline efficiency benefits that come from running multiple threads concurrently. A few details on this. A new instruction, yield, was defined in the MIPS-MT architecture. One variation of this instruction causes the thread to wait until a specific event occurs. While waiting for the event, the following instructions, which are the beginning of the interrupt service routine, are prefetched and stored into the instruction buffer. When the system event occurs, the thread can quickly resume execution. And when it resumes execution, the thread context has a dedicated register file, and there's no need to immediately do a context save or restore. I'll show this in a figure as well. This shows traditional interrupt servicing using some example cycle counts. When an interrupt comes in, it takes about 5 cycles to prioritize and take the exception. An additional 3 cycles are required to fetch the exception handler and have it ready to execute, and this is assuming a cache hit. Then you may need to save off some registers to free up some working space. This can take 20 cycles or potentially much more to do a full context save. After all of this time, you're finally ready to do what you came here for and service the interrupt. Upon completing that, you need to restore the registers that you previously saved off before you can resume running your original application. Compare this with the picture on an interrupt service thread. We're not going to be taking an exception, so we don't need to wait for it to be taken. The beginning of the exception handler has been prefetched and stored into the instruction buffer, so those cycles drop away as well. And because the thread context has a dedicated register file, the saving and restoring of the registers drops away as well, leaving you with the low interrupt response time and very low latency. A few additional notes on this. The thread scheduling policy can set the priority of the interrupt service routine. It could potentially be executed exclusively on the processor or at high, medium, or low priorities as desired. There's no reason to restrict this to one service thread. You could dedicate TCs to a few high priority interrupts, group lower priority interrupts into a common service thread, in addition to your regular application code running on the remaining TCs. This can also be generalized to cover some additional types of tasks. One example is having a monitor thread that is periodically triggered. This thread can query the state of the other threads on the processor and dump out information for profiling software to use. Another possible use is to have a thread dedicated to handling I/O coherence. If your system involves a lot of DMA activity that requires data to be flushed from the L1 data cache, you could have a thread dedicated to doing this flushing that is triggered when DMA activity begins. Now that we have seen some applications, let's look at some of the design decisions that were made on the 34K to enable this. The core supports a wide range of configurations, and there were design decisions made on the 34K. There are design challenges to ensure that the core performed well across the spectrum. In order to support the larger configurations, there couldn't be a large area or speed penalty from adding additional TCs. But you also do not want to penalize the smaller, more typical configurations because of that. This required some innovative design choices and forced careful consideration of when to replicate resources per TC. One example is the micro-TLB. On the 24K core, we had a 4-entry instruction micro-TLB to cache the latest address translations. Clearly, more entries would be required to service 9 TCs. But simply going to a larger array would have either impacted the core's frequency or required an additional pipeline stage. Instead, this is what we created. A private entry is associated with each TC. This entry gets selected in the preceding cycle when we're choosing which TC to fetch next. When the fetch starts, the virtual address is compared against the 3 shared translations and the 1 private one. This arrangement has a number of nice features. The lookup is still across 4 entries, so there's no speed penalty. When a single TC is running, it has access to a total of 4 entries, the 3 shared plus the 1 private. This is the same as it would have had running on a 24K. When multiple TCs are running, each one will have at least 1 entry and will be able to make forward progress. Having this dedicated entry removes some corner cases in the fetch unit and makes the control logic much simpler. Another design example is our instruction buffer. The 24K core had an 8-entry instruction buffer that decoupled the fetch unit from the execution pipeline. Execution unit stalls do not directly impact the fetch unit, and bubbles in the fetch pipeline are not necessarily seen by the execution unit. This is a fairly large structure, but there are several benefits from replicating it per TC. First off, the instruction buffer still serves to decouple the fetch unit from the execution unit. Additionally, the instruction buffer can keep the fetch unit isolated from dispatch decisions. That is, when we decide which thread to execute, that does not need to be immediately reflected in the fetch decision. This allows a simple fetch algorithm to be used. Another benefit is that it moves the thread selection point further down the pipeline. This allows the core to respond faster to events such as cache misses. This results in fewer instructions needing to be killed. This is shown in the following example. We are interleaving instructions from 2 threads, thread A in green and thread B in red. This figure shows the instructions progressing through the execution pipeline: the register file access, address generation, execution, memory stage, and exception resolution. Instruction B1 encounters a stall condition in the EX stage, for example, a dependency on a load miss. We stall for 1 cycle, detect that it's a long stall condition, and flush that thread out of the pipeline. The dispatch logic can quickly react to this situation, and it immediately begins selecting instructions exclusively from the running thread. Because the thread selection point is at the beginning of the execution unit, only 2 instructions needed to be flushed. If the thread selection point was at the beginning of the pipeline, there could easily be another 3 to 4 instructions in the fetch unit and instruction buffer that would also need to be killed. An additional reason for replicating the instruction buffer is to use it as a skid buffer. That is, instructions are held in the buffer for several cycles after dispatch. If a long stall condition is detected in this period, the instructions are still available in the instruction buffer, and the stall thread can be flushed from the pipeline without needing to be fetched again. Taking the same example as we had on the last slide, we have thread A and thread B interleaved in the pipeline. A long stall condition is detected on instruction B1. The 2 instructions from thread B can be flushed from the pipe, and the head buffer simply needs to be moved back to instruction B1. Because of this, the instructions are immediately ready to be re-executed. This has several advantages. The 2 killed instructions do not need to be refetched, and neither do any of the subsequent instructions in the instruction buffer. This can reduce power and reduce the pressure on fetch bandwidth. Additionally, because of the low overhead of killing instructions, the threshold for what constitutes a long stall can be set lower. Our threshold is that any stalls that we expect to last longer than 5 cycles will flush instructions back to the instruction buffer. If the killed instructions needed to be refetched, this level would need to be set higher. The instruction buffer was the largest optional structure that we decided to replicate per TC. A more typical design choice can be seen in the load data queue. This queue is a buffer within the load store unit that is used to hold information about pending load misses. Once the load data is available, it is also stored within this buffer until it's written back to the register file. On the 24K, we supported 4 outstanding load misses. The added threads running on a 34K provide additional data parallelism and can make use of more outstanding load misses. Thus, we added a configuration option to support up to 9 entries. On the 34K, this queue is also used to hold accesses to gating storage. Gating storage is a special region of memory that provides a mechanism for efficient data transfer between threads through the use of empty, full, and PV type semaphores. Having at least 1 entry per TC provides an easy way to avoid hardware deadlock conditions, and thus make this control logic simpler. The queue entries, however, are a pooled resource and are not tied to particular TCs. This allows running TCs to take advantage of the full size of the array, and there are not unused entries for TCs that are not running or not missing. Now that we've seen what the 34K is, what it can do, and how it does it, let's look at some numbers. The following results are all based on a core implemented in the TSMC 90 nanometer G process using nominal VT transistors. The core was configured to have 2 VPEs, 4 thread contexts, and instruction and data caches of 32 kilobytes each. Speed is over 500 megahertz with worst-case process voltage and temperature parameters. The area, including the caches, is only 5.1 square millimeters. Each TC costs less than 0.2 square millimeters, and a VPE costs under 0.3. The 34K has been proven in silicon and is currently available for general licensing. 2 of our lead customers have reported excellent results using the 34K. PMC reported a 300% improvement in voice over IP software versus single-threaded cores at the same speed. iVivity has said that by going to a system with 2 34Ks, it gave them 6 times the performance of their previous single-core system. To summarize, the 34K core features multi-threading extensions that enable it to excel at a wide variety of tasks. Dedicating hardware threads to critical tasks can reduce or remove the overhead of context switching and reduce the number of instructions that need to be executed. Adding dedicated hardware threads is possible on the 34K because of features that keep the cost low while preserving excellent performance. Thank you. No questions.
Any questions? Sure.
We have an entire stage dedicated, repeating the question, is asking what we did to the register file to enable it to work even though it's now 9 times larger. The answer is we have an entire stage dedicated to the register file access. So we were able to squeeze the access of the larger array into that cycle.
You also only support the 4 extra threads in this implementation, or is it all 9?
This is a particular implementation. A customer can configure it with up to 9. Yes?
That's right here.
Ando from Fujitsu. Would you explain somewhat more about your QoS or assigning the execution cycles to each TC?
Question was on the quality of service block. So this block is configurable by a customer. So we provide an external interface and a reference module a reference design that provides simple round robin or weighted round robin scheduling. A customer can choose to do a more involved policy manager that takes feedback information based on instructions completing, for example, and average that over a time window. For example, you can say that my audio decoding is going to need at least 500 cycles out of every 1,500. And as you're going through your 1,500 cycles, you compare where you're at versus where you need to be to execute 500 in your window. And if you're falling behind, you can increase the priority of that thread and cause it to execute, at a higher priority and more often, or even at exclusive level, and put other less critical tasks into a background mode.
Thank you.
Okay, thank you very much, Ryan.
Thank you.
Okay, so our third talk is another presentation about an ARM core. It's entitled Design of a Reusable 1 GHz Super-scalar ARM Processor, and Stephen Hill will be giving the presentation. Stephen Hill is a consulting engineer at ARM. He's been there for about 11 years. He's worked on several previous generations of ARM cores, most recently this Cortex A8, which he's going to describe. He's got an MS in microelectronic engineering from Southampton University in the UK. Stephen?
Thanks. Thank you. Yeah, so I work for ARM out of their Austin Design Center, so don't let my remaining English accent throw you off at all. And today I'm going to talk about the Cortex A8. In particular, I want to cover the reusable aspects of the design. Reusability isn't something I've seen an awful lot of academic work on, but those of us in the IP industry spend a lot of time worrying about it, so I thought it might be interesting. This is an outline of what I'm going to talk about. First of all, I'd like to give you a quick overview of the microarchitecture of the Cortex A8. Then I'd like to talk about exactly what I mean by reusability and why I think it was important for Cortex A8, what effects it had on the design flow and the microarchitecture, and then finally a few words about the interaction of energy efficient or low power design and reusability. So the overall goals of the Cortex A8 project were to deliver a new level of performance from an ARM CPU. In fact, the level we targeted was twice the performance of the previous generation. And the tricky thing as well was to do that for both tethered and mobile applications. And to do that as well while staying true to the values that ARM would like to be known for, which is obviously low power and reusable, flexible design. I won't spend an awful lot of time going over the architecture because that's been covered before. But the highlights are it's a dual issue, super-scalar, in-order machine. It's statically scheduled, and that's the first time that ARM has designed a super-scalar processor. It has a 13-stage pipeline, which gives us 9 or 10 useful gates per cycle between flip-flops. And so it's the fastest clocking ARM processor we've designed. It has a 10-stage SIMD acceleration unit that implements the Neon architecture. That accelerates both integer and floating point instructions, and it's the first time the Neon microarchitecture has been implemented. And we have an integrated level 2 cache controller as well. That's the first time that's been seen on an ARM core. So here's the pipeline diagram. Again, I won't cover this in huge detail because it's been seen before, but the whole left-hand side there is the main integer part of the machine, the 13-stage pipeline, and the right-hand side is the Neon SIMD acceleration unit. That's 10 stages long, and this diagram is obviously not trying to give you any idea of the physical size of these things, but it does get all the pipeline stages on one picture. Okay, so now to the main body of the talk, a little bit about reusability. So I think there's a lot of aspects of reusability that everyone probably understands already. Writing well-structured, well-commented code, providing a lot of documentation, providing tons of test vectors, that kind of thing. That's all fairly basic. What I'd like to cover today is actually the reusability of a microarchitecture. And by that, I really mean the ability to take a microarchitecture and re-implement it in different design flows, different cell libraries, different processes, and get useful results, get good results without investing a huge amount of engineering time in it. So it's really a measure of how well a microarchitecture can be reused and get good results for a reasonable cost. So why do I think that's important? Well, first of all, providing or producing a CPU with this level of performance takes a lot of engineering hours to build. It also takes an incredible amount of time to test. So to sell that as IP, we have to make sure that it can be reused across as many possible design flows and partners as we can find. Another thing is that reusability sort of translates to some flexibility in the microarchitecture in the RTL. So the way I look at things is we design building blocks that other people take and build into larger systems, and we can anticipate a lot of the use cases of those building blocks. We know how things will be reused most of the time, and we can make sure that those cases work well and are easy. But there's always going to be new and novel approaches to things. There's going to be ways of using IP that are invented after we've finished building it. So any more flexibility we can leave in the design that will help customers and partners make better use of it, the better. And finally, the fabrication process conveyor belt, Moore's law, slowing down a bit recently, but it still keeps advancing, and cell libraries have a similar thing. They get better over time, and design flows and EDA tools get better over time. So it's really important for microarchitecture to be able to adapt and keep up with those advances. Otherwise, it will get very quickly left behind by other architectures that can take on board all these new things. So there's a whole list of things that make a microarchitecture more or less reusable. I've listed some there. And it's definitely not a black and white, all or nothing thing. And I'm not suggesting it's possible to come up with a microarchitecture that you can reuse all the way from full custom, high-end design all the way down to FPGAs, say. That's just not practical. So what I am trying to say is if you look at the sort of the top curve there, where pick a quantity that you want to optimize. It doesn't really matter, but if you choose one quantity that you want to optimize for a particular design, then if you stick to one cell library and one process and one design flow, you'll get quite a narrow peak about which the architecture can be used. And what we were trying to do for Cortex-A8 was more like the bottom graph. We're trying to pull that peak apart a little bit, the range over which the microarchitecture is optimized, so that it can be reused on more design flows and more cell libraries. So the top curve might be a full custom design, say, mapped to one process. And that could be reused on other processes that have similar properties, optical shrinks and things. But if you wanted to take it and synthesize it, you probably wouldn't have very good luck. OK, so what effects did that have on the Cortex-A8 design flow? Well, when we started the project, we really wanted to make the whole design fully synthesizable at all performance points, because synthesis is great for reuse, right? It builds the design back up from the gate level from scratch every time you run the design flow. And it's really good for the design teams as well, because they get fast feedback about any changes they make. They find out what the power and frequency effects are. But when we started to look at the complete envelope of power and performance that we needed to hit, we found that most of that area was hittable by synthesis, but some of the very high-end, high-end for an embedded core, power performance trade-offs, we really needed to do something a little bit more advanced. So the plan we formed in the end was to make sure everything was fully synthesizable, to make sure that as many performance points and power points in the required envelope could be hittable through that route, but also allow some more sophisticated techniques to be used to hit a better power performance point. And the real key thing was to make sure that however much effort anyone invested in mapping this design, they'd get a good payback in terms of the end result. OK, so what effects did that have? For a start, although the design is fully synthesizable, we made sure that we partitioned it in such a way, right the way back in the RTL, that it could be implemented in a range of styles. So this is one design we did. You can see it's got custom regions and synthesized regions, sort of more random scattered areas there, and then some more structured tiled regions that I'll talk about a bit later. Now, although these divisions exist in the RTL, they're very easy to remove. The block boundaries can be just taken out, through a very simple synthesis flow. So the hooks are there to allow this to be used, but those hooks can be removed if they're not needed. And one interesting thing we saw is when we started to do synthesis, so Synopsys have a reference flow for this now, and when we started to do a lot of synthesis, we'd see that the standard cells would cluster in exactly the same way as the blocks are divided. Even if we'd flatten the whole design, the clusters of cells that belong to each unit and each block tended to stay in the same place. And obviously that's seeded by some of the pin positions and the positions of some of the custom blocks. But it was nice to see that the whole thing didn't merge into a sea of different colored cells. That kind of means that the boundaries and the interfaces are well set, I think. Okay, so a little bit more about the structured regions. So structured means that the code is obviously 100% synthesizable still, but then it's hand mapped to standard cell gates, and those gates are hand placed and then auto-routed together. So there's an example there. I think that's one of the ALUs. And you can see the different boxes are different standard cells, and the different colors represent different families of cells. So all the blue ones might be NAND gates, and the yellow ones registers or something like that. And this sort of technique is really good for regular structures, obviously, for data paths, queues, FIFOs, that sort of thing. It really helped us to control the routing and minimize the routing length, which let us then downsize transistors, which reduced cell size, which reduced routing length. So everything packs in very densely. It also allowed us to use a few restricted cells that we couldn't characterize well for synthesis. And I think the last thing here to note is that it was the relative placement of the cells that we recorded. So which cells are next to which other cells, or above or below which other cells, and not the absolute XY coordinate. That obviously makes the whole thing much more reusable between different cell libraries and different processes. Okay, so what sort of results did we see? So this is a little bit hard to read. The first line there is for an NVT-only cell library, and the rest of the table is for a mixed VT library. So this is one case where we had a unit we optimized for both approaches, and we were going after performance above everything else. So you can see from the NVT case, the tiling gives us a fairly good speed up. And then for the mixed VT case, synthesis catches up quite a lot, but it has to use a fair amount of fast, leaky cells to do that, so its static power is hurt a little bit. Okay, so generally developing a reusable microarchitecture. Measuring the performance of a microarchitecture is not too difficult. We can write a performance model and run it on some benchmarks and see what happens. And similarly, for sort of a good first pass at power and area and frequency, you can build the design once and scale pretty much to any process, to a first order of magnitude anyway. But for reusability, really, the design has to be built several times, okay? So one thing that really helped us there was ARM's partnership model, where we have several lead partners that are all building this design in different places around the world and feeding back a huge amount of useful information about optimizations for power and frequency and what works well with their design flow and what doesn't work quite so well. So that really helped us a lot. And one thing we noticed fairly early on is that these optimizations, although they tended to be not common to everyone, that at least 2 or 3 designs would have similar requests for how to make things better, so that once we started to fix those, the number of requests fell off quite quickly. And then there was different levels of reuse between all the lead partners, but the one common thread that everyone had was the same microarchitecture, the same RTL. So it was really important for us to try and, wherever we could and wherever we had a choice, if we could make a power improvement or a frequency improvement, we'd make that by modifying the RTL, by repipelining something or pushing logic to different sides of a flip-flop or changing the fan-in order of logic cones. Those were the best fixes because everyone could leverage them. Okay, so specific effects on the microarchitecture. We knew that high fan-out global signals were going to be an issue, so we basically eliminated them. Obviously, you've got a clock and a reset, but otherwise, we've got rid of all the global signals. And we did that by some fairly liberal use of small decoupling queues, and also by having a non-stalling execute pipeline. So once an instruction has got past the scoreboard, it'll progress at one pipeline stage per cycle until it writes back, until it completes. And there's no interlock signal or stall signal that ripples back up the execute units and tries to stall the front end of the pipe. And then the neon unit, as I said, it sits behind the retire point in the main pipeline. So once an instruction's passed the write-back stage, it has to complete. So neon, once it gets an instruction, it knows it's never going to be exceptional. It's never going to have to flush or cancel that signal in any way. In the less critical areas of the design, we tried really hard to make sure that the whole region would be synthesizable. Obviously, the more stuff that can be synthesized in any implementation, the better. It saves a lot of time. So one thing we did in the decode stages was to be relatively relaxed in the pipelining, and that cost us a little bit of performance, a trivial amount of performance really, but it meant that all the big instruction decoders, which are fairly nasty, random chunks of logic, could just be given to the synthesis tool in any implementation whatsoever. Obviously, the reason that isn't a particularly bad performance cost is that the depth of the decode pipeline is only really seen on a branch mispredict. In steady state, the depth of that pipeline is never seen in performance terms. Another good example is the embedded trace macrocell. That sits on the side of the execute pipelines, and it sends executed trace information out of the core. So it collects information about executed instructions and compresses it and sends it out to trace tools. Now that's a very regular structure with no stalling mechanism in it, so it would be great for some of the tiled implementation flows. But it also tends to be not critical. It tends to migrate to the edge of the design and sit somewhere where it doesn't hold out the X or Y coordinates of the die or of the macrocell. So again, we pipelined that to a depth where we knew it could be synthesizable, and in fact, all the implementations we've seen to date just go ahead and synthesize it, and it saves an awful lot of time. For the more critical areas of the design, we tried really hard to make sure that everything could be clustered together. So a good example there is the execute units. The two pipelines with execute units in them obviously have an awful lot of the single cycle architectural paths in the design, forwarding paths that have to operate in one cycle or the IPC would collapse. So one thing we did there was to be relatively relaxed at the front of the multiplier pipeline and let us take that whole chunk of logic out and put it slightly to the side and bus its operands to it. And we could cluster all the ALU pipelines and the shifters of the execute pipelines together in a very dense space and really reduce the amount of routing delay on all the forwarding paths. Another example there is the scoreboard. So the scoreboard, it doesn't only lock registers, but it tracks the position of all the writes in the pipeline. So as an instruction issues, it controls exactly which forwarding paths are going to be used. And all the comparators and the tracking and the shift registers that do that tracking are all smashed into one little area so that they can talk to each other quickly. So a few slides finally about the interaction of energy efficient design and reusable design. So obviously, as I said before, the most reusable power optimizations are the ones that are made in the RTL and the microarchitecture. And for me, at least, the single biggest optimization that we can make in the microarchitecture is to keep the thing as simple as it can be. Any extra complexity usually leads to burning more power. So we did a lot of performance modeling up front. We found that a statically scheduled in-order machine would give us the performance we needed, with a little bit of margin, actually, just enough to make it a safe bet. So as soon as we knew that, we stuck with that design. And one of the most interesting things for me was later in the project, as we were putting in more of the finer grain power optimizations, we found that the very predictable nature of the pipelines helped us a lot. So a good case in point is as an instruction issued, we knew which forwarding paths its operands would be on, or whether they'd come from the register bank, and we actually knew that several cycles before some of those paths had to operate. So we could just shut down all the ones that weren't needed. And actually, that saved us quite a lot of power in the register file in the end. Obviously, clock gating is still a big hitter for the RTL in terms of power saving. So there are 3 levels in the design. Architectural, which is a whole unit, like the embedded trace macrocell or the neon execution unit. Regional, which is a whole chunk of logic, like an instruction decoder, and that's optional. You don't have to put that in an implementation. But it does let you shut down a little bit of a higher level in the clock tree. And then local, which, as you'd expect, is individual registers or clusters of registers. So clock gating is important. Also now, obviously, leakage is becoming more and more of an issue. So there are hooks in the design to allow leakage mitigation measures to go in. A simple example of that is a lot of the interfaces across unit boundaries have extra tolerance to allow level shifters and voltage clamps to be put in where they're needed. And many of the units have an independent reset mechanism and clock tree so that they can be powered up and down as required. Okay, so we try really hard to make sure that power optimization is at the heart, is in the inner loop of the design flow, if you like, at ARM. So the RTL team has an awful lot of trade-offs to make. We're trying to trade off IPC in area and power and frequency and reusability, and that's a difficult enough trade-off to make as it is without trying to make it without full information. So we really try to make sure we can feed back an awful lot of information about power to the microarchitecture team. And this plot, which I hope you can see okay, is one of the mechanisms we use to do this. The little white specks are standard cells, and those are the cells that are burning the most power in the design, and then going down the scale of colors, the darker colors are burning less and less power. So this is the sort of thing that we'd use to investigate hotspots or to investigate where power was being burnt when we didn't expect it. And we obviously needed to use multiple vector sets to run this tool for different operating modes of the design. And one thing that I found interesting there was it was actually the quiet vectors, the vectors when the machine was supposed to be idle, waiting for instructions to turn up because of a cache miss, or data to turn up because of a cache miss, or it was in wait for interrupt mode. Those vectors revealed an awful lot of power bugs, actually. Those were some of the most interesting ones. Okay. And then this is the final slide I'll talk to before questions. This shows the progress for each unit on reducing the power that it consumed through different spins of the design. So on the left-hand side there, that's really when we started to close timing, and the right-hand side is when the chip finally closed timing. And you can see there's lots of little steps, and sometimes things don't always go well, and power comes back up as bug fixes go in, or someone finds a way to improve the frequency at the cost of a little bit of power. And each one of those little steps have probably got 20 or 30 sort of experiments that were done, and the good ones were kept and the bad ones were thrown out. And I guess the overall point I'm trying to make here is if you look at the solid line, that's the progress on the whole chip summed together. And in the end, although this design was done by a team that kind of, it's done low power design for a few years already. The designers already sort of think ahead of time how to make things low power. But even though that was the case, just these little improvements made over time managed to take 30% of the bottom line power of the design away. So my final thought there is that all these small improvements, it's really important that they get made in a reusable way, and that really means putting them in the microarchitecture and the RTL. So this is the summary, another view of the floor plan. I'll leave that up while I answer questions, if there are any. Okay.
Hi. So I have, I guess, two questions. The first is, how did you partition the logic into the synthesizable and the structure? Is that by, I mean, I know the architecture team knows the design, but you just went by the designer's knowledge of the design, or did you use any tools to do trial layouts and partition the?
So a lot of it was just trial and error. We didn't really have tools to help, so it was a case of spot regular structures in the design and try them out and see how well it worked. And one of the good things is that the guys doing that implementation, obviously, if you give something to a synthesizer, it kind of just works on it and tries to do its best, right? The guys doing that implementation, if they don't like what they see, they'll come down to your office and sit there and tell you that they don't like it and they want you to move some logic outside of that block so that they're just left with the more regular structures.
Okay, the second question is, once you did the partitioning, did you try to just synthesize and place and route that block as opposed to doing a structured thing? Because I still wonder that if you tried with appropriate pin locations on the boundary, if you try to do an automatic synthesis and place and route, it might still be as good as you have structured.
I didn't quite catch that. So did we try, if we left all the boundaries in and synthesized all the individual blocks?
Yeah, so if you showed one example structured block where you had done hand placed of the different data path units and then just did the auto route, right? The only thing you did automatic was routing.
Yeah.
Right? So I was wondering if you tried just to do that block alone, automatic from synthesis.
Yeah, no, we did try that, and yeah, it all depends. Well, all of it depends on the library, but generally for the regular structures, part of it is having a human there mapping the gates gives you a very regular, very predictable structure, and any time that we used an EDA tool, it tended to scramble things up just a little bit, so you'd end up with some routes that were a little bit longer, and then that kind of skews off the whole. If it's a regular structure, it skews off the whole thing a little bit. I don't know if that answered your question. I'll come and talk to you afterwards if it didn't. Sorry.
Thank you.
Will Strauss, Forward Concepts. After many years of working in Harvard architecture, what was the principal motivation moving to Super-scalar?
Performance, really. I think the embedded markets, if you sort of look at the big picture, the mainframe guys really develop a lot of early architecture, and then it comes to the desktop, and then it sort of filters down to the embedded space in the end. And we were really just looking for that next step in performance, and we tried a bunch of ways to get there. At single thread performance, I should say. And we tried a bunch of ways to get there, and that was the next biggest hitter we could find.
Okay.
I actually have a couple of questions. First one being, would you be able to tell us the power number for 1 gigahertz part instead of 600 megahertz?
If it's not there, no, sorry. Part of the reason for that is that it's very variable. There's a lot of ways to get to the 1 gigahertz number with different cell libraries and different processes.
Because I see like there'll be a big jump in the power if you try to achieve 1 gigahertz, right? If you try to go from 600 to 1 giga, right? So you'll see a big jump in the power number.
Yeah, it should scale with the clock, right?
Right.
And then depending on how you implemented it, it might be a little bit more than that even.
Second question is on the tiling part of your design, the structured data path design where you used relative placement. Is it like industry standard EDA flow, or is it in-house developed relative placement flow you guys used?
ARM doesn't really have any EDA development engineers, so all this stuff is industry standard tools. Sometimes they're used in a slightly wacky way, but they're all standard tools, and we're working with the EDA guys to make sure that way of using the tools is freely available and easily available to everyone.
Thank you.
Okay, thank you very much, Stephen.
Thank you.
So Hot Chips has a long tradition of mixing, leading edge industry designs with some degree of academic research, especially when it involves silicon. And such is the case with this next paper, or next presentation. It's called Towards Optimal Custom Instruction Processors, and it'll be presented by Dr. Wayne Luke. Dr. Luke is a professor of computer engineering at Imperial College of London. He co-founded the Hardware Compilation Group at Oxford University and also started the Custom Computing Group at Imperial College. His research interests include custom computer architectures and systems. Dr. Luke?
Thank you very much, Chuck. It is tremendous pleasure to be here, especially as one of the few academic representatives, hopefully to tell you one or two useful things that we are trying to do in our ivory towers. Hopefully that might be of some interest, and hopefully if any of you have any spare budget that we could help to spend, please let us know. So first of all, let me pay tribute to my co-authors. Kubilay Atasu is responsible for the optimal framework that you're going to hear. Rob Diamond provides the link from the theory to the hardware tools to the ASIC tools, which is absolutely essential. And Oskar Mencer, my colleague, who actually got his PhD from Stanford here, I thank him for proposing a presentation at Hot Chips for this idea, and thank him for not coming so that I could have the pleasure to come. So, a quick overview of what I'm going to say. So I'll begin with giving you a background of why we want to use extensible processes and an overview of how we do it, and then the design flow, how we go from a high-level description like in C or Java, go down to silicon. And then we talk about the really critical step, which is how to make use of some of the very powerful optimization tools which is now available so that we could actually make use of them to optimize, to get a really good instruction set and the resulting architecture. And then after that, I'll then give you the current tools that we have, give you an overview of what they look like, and then we'll tell you some numbers. And please bear in mind that these numbers represent a relatively early stage in our research. So that would mean that although they look promising, they probably do not represent what we could really achieve if we spend a bit more time on that. So let me start with some motivation. For that, I think I probably should thank Justin Redner, who gave a really good keynote talk. And if you remember, during his talk, he put up this slide, and I have to apologize to him because I have a really not very good digital camera. So you might remember that he put up this slide, and I got him in there as well, just in case people don't remember him. So you'll see that the red bits here correspond to potential gains that one could obtain by new instructions. Okay. Now, obviously, if you only have one core, then perhaps this effect might not be very much. But when we move to multi-core, which I think really is what a lot of this presentation in this conference is about, then you could see the potential gain with these new instructions would really be quite tremendous. So one of the questions is, how do we get these new instructions? Can we obtain them automatically? And how optimal could they be? Okay, so my talk here is try to address these issues in understanding at least one way of getting these new instructions that Justin mentioned in his talk. Okay, now the idea is that the new instructions will be implemented by this custom instruction unit, which is in addition to the base instruction unit. Okay, so again, if you look at Justin's talk, now he has a baseline processor. So the red part here corresponds to the baseline processor, and the blue part here corresponds to the custom processing unit that would be required to support the custom instructions. Okay? So the basic idea is really how to partition the data flow graph that corresponds to some user program so that the data-intensive part, the computationally intensive part, could then be allocated to this custom processing unit in order to speed things up. Okay? So that is the basic idea of our framework. And you could see that it has the attraction that it can be, in principle, add to any existing processors, whether they are commercial or academic and so on, because we are really focusing on this bit. Okay? So that is at least the basic principle. Okay, so there's actually quite a lot of previous work on how to develop custom instructions for application-specific processors. And I do apologize that if your favorite approach is not included in here, because I only want to use 2/3 of the slide for describing that. So these are all focused on various aspects, and including some of which actually described in Hot Chips two years ago. But I think perhaps not all of them address the 3 issues that I'm trying to cover. The first of which is, well, how to ensure the optimality and robustness of the heuristics that we're going to use to achieve the choose instructions to optimize the architecture. And also, how do we make sure we have a complete tool chain from high-level description of the application program down to the actual silicon. So how can we actually demonstrate the feasibility of this tool chain? Okay? And then the last probably would be of greater interest to researchers in the audience. How do we provide an infrastructure so that we could explore different approaches, different strategies in order to achieve this customizable processor design framework? Okay, so what I'm going to do quite quickly is to describe a particular approach that our research group has been looking at. And the idea is, first of all, in order to address the optimality and robustness of the heuristics, well, the answer is, why don't we do not use heuristics, but actually use some of the optimization techniques that's been now available in form of industrial tools. In particular, we are looking at a technique called integer linear programming. Well, that has the advantage that there are some existing industrial tools such as Cplex, which have been used to optimize quite big problems. However, the drawback, if you like, is that, well, we need to be able to express the optimization of the processor in terms of constraints that are linear and could be expressed by integers and so on. So there is obviously some trade-off as to the kind of constraint that can be captured by this framework. Also, we look at a complete tool chain from high-level description down to the lowest level implementation. Although we would make use of existing tools, either commercial or academic tools, so that we will focus on the bit that we could add the greatest value rather than try to redo things that other people have already done a good job. And what we aim to do is to provide or to contribute to an open reserve infrastructure so that one could explore different ways to synthesize custom instructions and also finding ways to automate. What are the degrees of automation and to what extent real designers can influence the automation so that we could get the best trade-off in terms of optimality and in terms of designer productivity. So how to get the best trade-off between these two concerns. Okay, so the current tools that we are using is based on Trimarant to build the custom CPUs, or at least the framework that I'm going to describe today. And we also use, I have not put it in here, but we also use an industrial optimization tool called Cplex in our optimization framework. And we also develop our own synthesis tools, which is based on both the Synopsys mapping tool and also some of the custom library blocks from Cadence. And I'll talk about that a little bit more in a minute. Okay, so this is the overview of our design flow. So we start off from a high-level description in C, and then there are two key steps in our optimization framework. The first is try to generate templates from the application, and I'll explain a bit more about what these templates are. These are basically templates based on the data flow graph in the user program. So generate the templates and then select them based on some area constraints also provided by the designers. Okay. And then after that, then we'll need to generate the custom unit that targets the custom instructions. And also we will generate the base processor that we would use to host the whole architecture. And then the result that could then be sent to ASIC tools, or if you like, especially for universities that might not have a big budget, we could replace the ASIC tools by FPGA tools when that is appropriate. And then we could get some area and timing results. Okay, so this is a really high-level view of the data path that we're going to synthesize. So essentially is the register file, which has limited number of input ports and output ports. So the number of input ports and output ports could be part of the constraints that we send to the optimization framework. Okay, so you could see the input register there and also the output register over there. And those will connect to other parts of the architecture. And then this part would then be linked to the various operation units in the custom data path. Okay? And notice that these custom units may or may not just contain to the input register. It could also directly connect to the register path, register file, and so on. And there would be various pipeline registers to make sure that the speed of this custom unit will match that of the base processor, so that there will not be a bottleneck in the resulting implementation. Okay, so how to obtain optimality? Okay, so the key idea is really to try to optimize for both speed and area. So at this stage, we are not talking about power consumption yet, although I believe that it is possible to extend the framework that we described over here to cover other constraints, such as power consumption. So we try to minimize the schedule length of the program by minimizing the length that of the longest path in the data flow graph. Okay? Now, we want to do that not just to optimize for speed, but also to optimize for the area as well. And therefore, there would also be constraints about the feasibility of the schedule that we're going to have. So there are various constraints such as convexity, so that if there are some output in the middle of the graph, then that might be a problem because that might be linked to other blocks in the data flow graph that we may or may not know how much time it takes and so on. So there are various constraints when we try to synthesize for our templates in our system. So we have the convexity constraints. We also have the speed constraints to make sure that the result of the design will match the critical path of the base processor and so on. And we might need to insert pipeline registers where necessary. We also have the fixed data bandwidth constraint that correspond to the size of the input ports and output ports. And we also need to take into account when we try to optimize for the implementation. Okay, and the key step, the optimization, well, once you formulate this model, and I should emphasize that when we say optimal, we meant optimality with respect to this model. Okay, so you have to believe us that this model is appropriate because this is really what optimality is relative to. Okay, so once we formulate this model and we are happy that it could capture the optimality that the designer wants to achieve, then it would then be a matter of actually making sure that these constraints as defined over there can then be solved by the tools that are available. In order to do that, we have two steps. One is called template generation, and the second one is called template selection, which I'm going to describe over here. Okay, so template generation corresponds to analyzing the data flow graph so that we could identify patterns that could become candidates to be supported by custom instructions. Okay, so for example, if one could identify these blue blocks and so on to be a particular candidate, then we could collapse these nodes into a single node. And then we could repeat that to identify such patterns in various subgraphs in the data flow graph. And this process here is being solved by this integer linear programming framework. So I do apologize that this is the alias, that ILP doesn't mean instruction level parallelism. In this case, it meant integer linear programming. Okay? So we actually applied this optimization repeatedly, okay, until the objective of the constraints are met by this process. After that, then we have a template that corresponds to the possibility of custom instructions. So what we want would then be identify the mapping between the templates and the actual instructions. And once we identify this mapping, what we have would then we group into different classes of templates. Each corresponds to particular custom instructions. And because now we identify the custom instructions and the corresponding resources that implement the custom instructions, we now can calculate the speed up for each group of these classes. Okay. So once we get the classes that could implement such templates, we know the speed up, then the remaining question is, can we satisfy the area constraint? Okay. So in order to do that, we formulate this as the knapsack problem so that we could choose the instructions that execute both the fastest but would also fit into the required area that we could see as bounded by the knapsack. Okay? So again, this problem can be formulated as an integer linear programming problem that we could then try to calculate the maximum speed up within the area constraint. Okay? So you could see that we use the integer linear programming optimization in both the template generation, which try to optimize the speed, and then we also use it in the optimization of the area with the maximum speed in mind. So we do it in these two steps. Okay, so the optimization flow is described in this diagram. And you could see that the application in C or C++, we make use of the impact front end, which is also part of the trimaran framework. We get various control flow and data flow graph information, and then we now fit into this bit, which is the bit that's been developed by Kubilay and by Rob. And they look at this template generation side, which takes the data bandwidth and various convexity constraints into account in this step. And then the potential gains and so on would then be sent to the second step, which is the template selection, which takes into account the area constraint as supplied by the designer. And also the area of various resources for the custom instruction is obtained by getting out to the synopsis flow so that we could have some estimate of what the area would be like. And then this step would then, after we achieve a potential results that should satisfy the constraints that we provide, then we would then turn to the back end where there are various machine descriptions and other steps in order to replace the instruction for the base processor by the custom instructions developed by these two steps. And then we could then use the LCore backend to do the scheduling and register allocation and so on. And then we could then get the assembly code and various statistics about the area and time and so on. Okay? So that is the design flow that we are using now. Okay, so let's have a look at the actual design tools that are developed by us. So the idea is we have a way to explore different designs very quickly so that the designer, instead of focusing the effort on optimizing very low-level things, the designer could focus on defining the constraints and very quickly look at the consequences of these different constraints so that he or she can then decide whether the implementation is appropriate for the particular requirements. Okay? So we aim to provide a very fast loop from high-level description to implementation. And I'll show you in a minute that one could actually generate tens or even hundreds of processor descriptions in order to look at what would be the most appropriate for the particular application. So in order to support this framework, there is a processor component library that has all the major components like ALUs and adders, multipliers, and various blocks, which is captured in structural description. And currently, our base processor is a simplified version of MIPS, which is now well known because of the textbook by Patterson and Hennessy. And we use that as our base processor on which we could then add various custom instructions and also augment the basic architecture by a more flexible architecture. For instance, we could define different levels of pipeline stages in the microarchitecture. And then we could then evaluate using the ASIC design flow in order to obtain some area and timing numbers. Okay, so this just shows that from the compiler, we generate various custom data paths, which we can then merge and add various state registers, processor interfaces, and so on to get our custom processor unit. We also have the processor component library, which corresponds to ALUs and various execution units, which this custom processor could then link to various blocks in order to actually get the actual description that we have. So the implementation currently is mainly based on various scripts written in Python, and it provides a meta language for describing the processes. And really what it's doing is to combine various RTL blocks together. And for performance critical blocks, we wrote our own module generators in order to get a good description. So the advantage of this framework is to allow us to generate a lot of designs very quickly so that we could allow the designers to change the constraints in order to find out what might be the most interesting implementation. And in addition to run our framework through ASIC design tools, we also adapt the backend of our system to FPGA design tools so that we could actually run the CPU and the memory and the I/O and so on. We could actually run that on an FPGA. So the ASIC result that I'm going to show you has not actually been fabricated. But we actually have made sure that the result from our design does in fact work because we run it onto an FPGA prototype. So in order to try out and to illustrate our approach, we have a look at various encryption applications. So we look at AES, we look at DAS, we look at MD5 and SHA and so on. So the base processor is essentially a 4 to 5 stage pipeline implementing the MIPS instruction set. And it's around 0.225 millimeter square area with 200 megahertz speed. It's all, so all these processors are all synthesized, so we haven't really laid out ourselves. So it's all use industrial strength tools to synthesize these things. So single issue processor, simple register file, 2 input ports, 1 output port. So it's the very standard processor description. And then the resulting custom processors are synthesized to 130 nanometer library, making use of Synopsys design compilers and also the Cadence, SOC encounter, and so on. And as I said before, we also take the same design flow, but just change the backend so that we could synthesize to Xilinx FPGAs for testing. So we do make sure that the result actually works, at least functionally. So this is just a chip plot to show what it's like as generated from the ASIC tools. We find that as far as for the AES encryption is concerned, the custom unit is basically take around 35% of the area. It's mainly just one instruction. And the next slide actually shows roughly what the corresponding blocks of the layout is like. So over here, that is the register file. Since we actually do not have the register library block, right now this bit is actually implemented by some SRAM blocks. And the custom instruction units are actually over here. And because it is dictated by the place and route tools, we don't actually dictate where they put the logic. So this is what they tell us, that this custom instructions are implemented over here. So the area for the custom unit for the AES encryption is around 35%. And although it's 35%, it actually provides 76% reduction in number of cycles. So I think one could say it is a good trade-off because you only increase area by 35%, but you actually reduce number of cycles by 76%. Okay, so this also gives you some description of various applications, as I said, from AES, DAS, MD5, and so on. Turns out that the AES gives the greatest reduction, whereas MD5 give you not so good reduction. Probably some of that was because it's a rather more complex design. And perhaps right now our design flow is not as optimal as it could have been. So we hope that all these results could be further improved in future work. As far as timing is concerned, I should explain that each dot here corresponds to a separate custom processor that has been synthesized by our framework. Okay, so the zero line there corresponds designs that meets the 200 megahertz constraint for the base processor, and there are actually 48% that already meets the speed of that. So the dots below that corresponds to processors synthesized by framework but do not meet the speed constraints. We expect that it would something like that because we did formulate in the optimization criterion that the result should meet the speed constraint. So it is useful to see that most designs are indeed like that. So as far as the area and speed are concerned, for the maximum speed up, one could get so this 23%, 93%, and so on corresponds to additional area that is above the base processor. Okay, so the chip area is given by the deep blue blocks, and the 23% of SHA correspond to the additional area that is required to implement the custom units and so on. So a quick description of our current and future work. So there are really a number of those. The more exciting one corresponds to, for example, extending the current approach so that we could support SIMD style instructions, which could be useful for a lot of multimedia applications. And of course, you will notice that currently we are focusing on encryption applications, and we hope that we will be able to extend our approach to cover various multimedia, multi-core applications, and indeed supporting power consumption as part of the optimization step. Okay, so I think these are the key points of our design approach, and currently it shows good promise without spending too much time on the low-level optimization, and we hope that I will be able to report next year or in a few years' time how much further we could push the idea of using optimization tools in custom instruction application design. Thank you very much.
So I guess I have one question. Sorry to yell at you there.
Okay.
Let's see, in the template generation phase, how often are you actually finding things that wouldn't be sort of obvious just by looking at the kernel of the code itself and doing it by inspection? Are you actually discovering things
Yes.
you wouldn't have seen?
Very good question. I think the the question is to what extent the optimization framework, to what extent can visual inspection or looking at the data flow graph could actually allow the designer to extract the custom instruction manually rather than going through the optimization framework? Well, the answer is, of course, if you're the designer, you know the application very well. You will do a very good job. On the other hand, if you have a big design, then it is no longer obvious whether the choice of the designer is necessarily optimal. So I think there are two reasons why we want to do this. A is that it is guaranteed optimal with respect to the optimization model that we have. Whereas if it is designer, it might be based on previous experience, which would be good, but it might not be optimal with respect to the model. Secondly, it might be relatively tedious, might be error-prone. So what we want to do is automate this step. And of course, designers could still try to do it manually and compare the manual designs with the automatic results. And indeed, and that's actually one interesting thing about this framework is that because the designer can actually control the optimization by defining different constraints. So instead, once you optimize, once you spot some of these blocks, you could actually try to express your experience as part of the constraints on the automatic system. Okay, so it could actually really be a co-design between the experienced designer and also the optimization framework. So it actually assists the optimization framework so that it will sort of look carefully at the choice of you. And then it might come back and say, well, you know, yours is quite good, but not as good as the one that I find. So, and then you could then decide, right, I still think I need to, you know, use mine because my library or something else, you know, is, you know. So the designer could still have their own choice. What I described there is an alternative, which could offer to the designers to see whether you like or not.
One quick question over here.
Yeah, I had another quick question. How long does this cycle take to go from the C to the custom processor, and which phases in that in the flow take the longest? Is the code analysis, data flow analysis take the longest? The template generation and selection? So how long does the flow take, and what stages are the most time-consuming?
Right. Well, obviously, the answer would depend on what application that you have. So for a simple application, defined by the size of the data flow graph. Okay, so for instance, for AES, then it probably would take half an hour, a few minutes. So the template, so the time that takes longest is the template generation step, because you could see there is a loop that we apply optimization repeatedly or recursively in order to look at all the subgraphs and so on. That takes the longest step. Having said that, I think one of the more complex examples is the MD5, and I think that has more than 1,000 nodes in the in the data flow graph, and I think that would still take. I think the longest thing is probably up to a day or something like that, but that's probably because we have not optimized some of our scripts. So bearing in mind that this is really a research tool that is still evolving. So I think if we actually try to optimize it for industrial use, I suspect that one could probably able to make sure that most of the design or the initial exploration stage would not take more than, let's say, half an hour, that sort of time.
Okay, thank you very much.